Welcome to the SEG Europe Regional Advisory Committee's webinar series, Geophysics for Today and Tomorrow. Dr. Adriana Ramirez, Chair of the SEG Europe Regional Advisory Committee, and myself, Lori Weitzel, will serve as your host for today's webinar. Before we begin, the model for this webinar will be a short presentation followed by an extended question and answer session. During the question and answer session, if you'd like to ask questions, please raise your hand in the webinar interface, and I will adjust your settings to allow you to ask your questions directly to the presenter. Alternatively, you can enter your questions into the question and answer box at the bottom or top of your display. So our presenter for today is Dr. Cedric Schmelbach. He is a graduate of the University of Zurich in Switzerland and Uppsala University in Sweden. He also, including a visit to Rice as a PhD. After graduating, Dr. Schmelbach worked as a postdoc first at the University of Potsdam in Germany and later at Free University in Berlin, Germany. He joined ETH Zurich in 2012 and currently holds a position as senior scientist and lecturer. Dr. Schmelbach's research is centered on seismic exploration at different scales, including near-surface seismic methods, acquisition and processing of seismic multi-component data, seismic spatial gradient and rotational motion measurements, and multidisciplinary investigations of the shallow subsurface. More recently, he became involved in space exploration and is a member of the science team of NASA's InSight mission to Mars, as well as the LISA Consortium. Dr. Schmelbach is a member of EGU, AGU, EAGE, SEG, and DFG. He holds offices with the EGU and is editor of Advances in Geophysics. So without further delay, please welcome our presenter today, Dr. Cedric Schmelbach.
So thank you, Lori, very much for this introduction, and thanks to SEG for giving me the opportunity to talk about our research. So my name is Cedric Schmelbach, and today in this webinar, I'd like to talk about using seismic methods to investigate planetary objects, so with a focus on Moon and Mars. Obviously, this is work done with in collaboration with many people that I want to acknowledge here. So please grab your cup of coffee and tea and follow me on this tour through to our nearest neighbors in space. So I thought for today, I picked two case studies that I'd like to talk about. So the first one is revisiting Apollo 17 active seismic data that were required during the Apollo missions, and actually showing you the value or the power of using latest technologies to take vintage data and squeeze out things that were not possible to extract from this data once they were acquired and processed the first time. Then I want to move on to Mars and talk about what I would call the first active source seismic experiment on Mars as a part of the ongoing InSight mission that is right now operating a seismometer on Mars. Then as a kind of outlook, rather, I'd like to move on and talk about next generation seismic equipment for space exploration. So we're focusing on measuring 6 degrees of freedom, so rotations and translations, and the value of these measurements for planetary seismology. And then make a step further and talk about something that could be seen as a new application field of seismology. So looking into gravitational waves, and in particular looking at the LISA satellite constellation and interpret that as a gigantic seismometer. So before talking about these missions, I'll briefly review the history of planetary seismology. So seismology turned out to be a very powerful technique on Earth to study the interior structures, in particular because of its penetration depth and high resolution at depth. So the value of seismology was recognized early on in planetary exploration. So seismometers were part of the very early missions to Moon, for example, the Rangers 3 to 5, that all actually failed. But then very successfully, seismometers were installed on Moon during the Apollo missions. So you see here on this image, astronaut Aldrin, just after installation of the passive seismic experiment package that operated a seismometer for 21 days on Moon. But then the following Apollo missions installed 4 stations on Moon that operated until the end of September 1977. And what is also very interesting is that 3 active source seismic experiments were carried out during Apollo missions 14, 16, and 17. And I'll come back to the one carried out during Apollo 17 later in this presentation. So it took a couple of attempts to install seismometers successfully on Mars. For example, the Viking 1 mission landed on Mars, but then failed to unlock the instrument. So Viking 2 was for a long time the only seismometer that operated on Mars. And you see here an image of the lander and the arrow pointed to the seismometer. But as you can see here, the seismometer was installed on the lander. And so it is believed today that it was mainly recording signals due to the wind, so showing a very high sensitivity to wind, and maybe very little or none signals that actually came from Mars. So it wasn't until the InSight mission to Mars that a 6-axis seismometer was successfully installed on the surface on Mars in December 2018. And I'll come back to that in a moment. And I think another noteworthy seismic experiment in space was the Comet acoustic sounding experiment carried out on Comet 67P, so Jury, where people could, with the help of a seismic experiment, at least constrain the elastic parameters of the comet that you see here on the bottom. But with that, I'd like to move on now and get to Moon and talk about the reanalysis of data that was acquired during Apollo 17 mission to study the elastic structure of the lunar crust using a new technology in seismic exploration, so seismic Wavefield gradient analysis. Now, before talking about the experiments on Moon, I want to head back to Earth and actually briefly explain you what seismic Wavefield gradiometry is. So what you see here is a layout, a dense layout of conventional geophones. And with the help of this picture, I want to explain you what I mean by gradiometry, which is concerned with the spatial gradients of the seismic wave field. So conventionally, we place one sensor and measure the particle velocity or particle acceleration at one point and analyze this data in seismic exploration work. But if we place 2 sensors close to each other, by close I mean at a fraction of the wavelength that is of interest, we can compute, for example, here by finite difference approximation, the spatial wavefield gradient of the gradient of the wave field. And this actually opens up new avenues to process and interpret the seismic data. And I will come back to what can be done with this type of gradient measurements complementing the conventional translational measurements. So one interesting property is, if we are at the free surface where the vertical components of the stresses are 0, actually the horizontal gradient of the vertical component motion corresponds to the rotational motion around the horizontal axis, as I've tried to illustrate here. So that means if we place conventional geophones at the surface close enough to compute the spatial gradients, we can estimate the curl component of the seismic wave field. And this opens up very interesting approaches to interpret seismic data. I'll call that type of observable array-derived rotations later on. So I thought I would discuss 2 applications of gradients that are of relevance to the study that I will talk about later. The one is using the gradients to estimate the local instantaneous slowness. So what you see here on this equation is on the right-hand side, the spatial gradient of our V, so our particle velocity measurement, for example. And on the right-hand side, you see the time derivative. So that could be the acceleration, and we have the local slowness that as a proportionality constant here. So if we solve that equation for, say, a given array, we can estimate at a point the local slowness. I want to illustrate that with an example. So what you see here on the bottom are layouts of 3 × 3 sensors. They're just 1 meter apart. The yellow boxes that you see on the bottom left. And then if you look at the seismic data on the right, you see the wiggle traces. They show the recordings that we have for the central receiver. Now in color in the background, I show you the slowness that was computed each time just for a layout of 3 × 3 sensors, and say giving us a instantaneous local velocity or slowness estimate at the center of the array. And now it's interesting to compare that with what we would call a more conventional array type of analysis. So if we had a long line of receivers, we can then fit lines to the observed phases and estimate apparent velocities. This is done here now for this surface wave, and you see by just fitting a line to these arrivals, we get a velocity of 270 meters per second, which is very close to this instantaneous local estimate of the slowness. And this kind of highlights that we can replace a long array by a very small, dense layout of receivers and a very local measurement if you have gradients at hand, and can then carry out processing, like, for example, estimating local slownesses with this new type of arrangement that would conventionally need very long layouts. Now, a second application is decomposing the wave field, so helping in analyzing the wave field or understanding what type of waves we have recorded. And to illustrate that, I will come back to, we'll show you here the Lamé's theorem that shows you how we can decompose within a homogeneous medium the wave field U into a P wave potential and a shear wave potential. Now, you may have seen this, the application that I discussed here before in finite difference simulation. So if we take now our wave field and if we apply the curl operator, what you see here on the bottom left, then the P wave potential will drop out because it's curl free, and we're left with the shear wave potential. So this is a way, as I just said, in finite difference simulations, for example, to isolate P wave or shear wave. Now, if we have sensors at hand, as I discussed before, this could be arrays, as you see with this photograph showing you the yellow boxes, conventional geophones, or if you have dedicated sensors like a rotational sensor to just measure the rotational motion, so the curl of the wave field, we actually do isolation of the shear waves. So with the help of these array-derived rotations, for example, we can decompose our wave field and isolate shear waves that can help in the interpretation of the wave field. So now let's move back to Moon and to the Apollo 17 data. So what I show you here on this image actually is one of the geophones that was installed on Moon right next to this reddish flag. So during the Apollo 17 missions in 1972, a layout of 4 geophones in a Y-shaped configuration were placed on Moon with about 60 meters separation between the geophones, as you see that here on the bottom. And as I showed you before, geophones here were marked with red flags. And then a total of 8 so-called explosive packages were placed on Moon by the astronauts. And these explosive packages, they have, say, about 50 to 2.7 kilograms of explosives. And they were placed in distances between 100 meters or so to up to 3 kilometers. And once the astronauts had left Moon, these explosive packages were fired and the seismic data recorded and then transmitted back to Earth. Now, when the data arrived, actually already for the campaigns that were done for the Apollo missions before, the people realized that the wave field looks quite different on Moon compared to what we were used on Earth. What you see here is the recordings of one of the explosive packages for the 4 geophones. We see the P wave first arrival, so the very first energy reaching the geophones, marked by the dashed line. And then we see a very long wave train that lasts actually for a few seconds. And the difference of this data and characteristics compared to Earth data maybe becomes more obvious if we compare that with a measurement on Earth. So what I show you here on the left-hand side is a dynamite shot recorded in a karstified area in Switzerland. So 60 grams of dynamite were used here. And if you look at the wave field, we see distinct arrivals like clear P wave first arrivals. We see later high amplitude surface waves, maybe even some reflections in the data. And they also observe that the energy, the amplitudes decay to ambient noise level probably after several hundreds of milliseconds. What's not fully shown here on this record. But if you compare that now with the Moon data, and I marked a time window of the same size or same length with the red box here, you see that actually energy lasts or bounces around in a subsurface for much longer than what you would expect on Earth. So for several seconds, and individual arrivals are very hard to identify. Actually, it's almost impossible to see any clear arrivals in this data. So the explanation for this type of data that we see here is that we are looking at a wave propagation in a highly scattering medium where we have essentially no absorption. And if you compare that in this simulation to a homogeneous medium, which is probably an oversimplified case for Earth, we see that on the left-hand side, we have clear arrivals that disappear after some time. But if you look on the right, we see that energy is scattered, bouncing back and forth in the subsurface for a very long time and is recorded at the receivers for much longer than what it would be recorded on Earth. So these data were very difficult to interpret at the time in the 70s, and actually only P waves were, so the very first arrivals were interpreted. But now we went back to this data from the archive, and once this idea of computing rotations from arrays was here, we thought that it would be worth looking into these data because of this small array that was used and to see whether it is possible to compute array-derived rotations. So you see that the geophones were relatively close. By computing the horizontal component of the vertical derivative of these 4 geophones placed on Moon, we should be able to compute the rotational motion around the 2 horizontal axes. Now, ideally, for future missions, we would like to have a single instrument actually providing us this value, and I will come back to that idea later in this presentation. But now let's look at what we can do with these rotational motion measurements. So what you see here on the left-hand side is an analysis of the data. You see on to the very left, the central trace recording for 2 explosive packages. And then the other trace that you see here in the center of this graph is actually the sum of the rotational energy computed for the array. And we see that there are distinct increases in rotational energy at some times, and these were interpreted as the arrival of shear waves at the geophone layout. And it's interesting to compare that with the original recording, but it's very hard to actually see this type of arrival. So computing the rotation really helps to further decompose the wave field, understand the wave field. And now you see in the background the color that shows the instantaneous slowness that is computed in the way as I discussed before. And what is also interesting is that slowness also provides the propagation direction, so it's a vector. And if you look at the propagation direction of the first arrivals compared to the line between source and receivers, which is marked by the dashed line, we see actually that we can resolve the direction from where the waves arrive. So what has been done here, or what we've done here, is picking all the different increases in energy level, interpreting them as P and shear arrivals, and plotting them in an offset, so source-receiver offset versus travel time plot. And you see in black, these are the peaks for the P wave arrivals. So this is actually the analysis that has already been done in the 70s, and we can invert that for a 1D P wave velocity model. Now we see in red all the shear wave data, or say the later arrivals that could clearly be seen in the data, and we see that they also align actually and provide information on the subsurface velocities. We, for example, see the latest, lines that we see here is probably really the pure shear wave arriving at the receiver layout, and we see other coherent lines or continuous lines that are waves that traveled probably a part of their path, not as shear waves, but as P waves, so were converted waves at some point in the subsurface. And what is also interesting to see is the lines that you see around the points, they mark this instantaneous velocity that we can compute. So the color that we see on the on the left-hand side, and we see that in particular for the later arrivals, this instantaneous velocity that is computed from the array is parallel or almost parallel to the line that we fit to the arrivals to the dashed lines. So that shows that actually this array-based, local gradient-based analysis is very comparable to array-based analysis for velocity. But now actually what we wanted to do is taking all this information here and invert this for subsurface velocity model. Just to remind you, what has been done in the 70s is analyzing or interpreting this data in terms of a P-wave subsurface velocity model. What we have done here now and added is computing also the shear wave velocities as a function of depth. And you see that this is the red line here. So this is the first time that a shallow shear wave velocity profile could be computed. This based on the fact that we estimated array-derived rotations, and complemented here then the p-wave velocity model. You see that these are data that show relatively low velocities. We can compute Poisson's ratios that are relatively high and probably indicate that we have heavily fractured subsurface material. And just to remind you, this model here was built actually with data recorded with 4 receivers from 8 shots, so 32 recordings are used here to compute this subsurface model. And as a last step, we try to verify the model by doing some finite difference simulations. So what we did is taking the 1D velocity profile that we had computed from the arrival times, and we added stochastic variations to simulate the strong scattering that is observed in the data, or thought to be the element that really characterizes these data. And what you can see is we can actually reproduce these clear shear wave arrivals in the data. We can identify them in the data even with this synthetic exercise. So that shows that actually, even though we have this strong scattering medium, it seems that the layering is still resolvable. So with that, I'd like to finish this journey to the moon and showing here also this image from Tintin, Explorers on the Moon, where he's together with Captain Haddock. And I think it's very interesting to note, or nice to note, that this study was done in the this comic was produced in the 1950s, and it shows how much before actually the moon missions, the ideas that Hergé developed or investigated, and all the ideas that he had, it was quite, I think, very interesting to see that this happened so much before the actual moon missions. So with that, I would like to move on to InSight and talk about what I called before the first active source seismics on Mars. So the InSight mission has the scientific goals to help us in understanding the formation and evolution of Mars, and with that actually help in the understanding of how the rocky planets formed, and ultimately how the solar system formed. And a further goal is to determine the level of seismic activity on Mars. There are 3 key instruments on InSight. One is SEIS, a seismometer package, then HP-Cube, a heat flow probe, and RAISE, a radio science experiment. InSight was launched the 5th of May 2018 and landed on the 26th of November 2018 in Elysium Planitia. And you see here on the right-hand side one of the very first images that InSight took. And you also see a high-rise image, so from a satellite that is orbiting Mars and taking high-resolution images, photograph an image of the landing site. So on the next slides, I'd like to discuss those instruments that are actually important for the study that I want to discuss here. So the first is this seismometer package SEIS that was actually deployed directly on the surface of Mars as a direct consequence of the Viking 2 experience. So the seismometer actually consists of 2 instruments, so-called very broadband VBB 3-component seismometer that is measuring low frequencies from tidal to around 10 Hertz, and the second instrument, the short period instrument that is MEMS-based, that is measuring frequencies between around 0.1 Hertz and 50 Hertz. Then these instruments are covered by a wind shield to protect it from the influence of wind and temperature changes. So this also as a lesson learned from Viking 2 mission. And then this instrument is placed on a leveling system that allows to level the system, the seismometer constantly. The second, before talking about second instrument, I thought I would show you some of the data that has been recorded so far, in particular the first likely Mars quake that was measured on 6th of April 2019. So that's Sol 128, so the 128th day on Mars. You will hear a sonification of these records that show you first Mars wind, so the signal that is most often recorded by this instrument, a likely Mars quake, and then the signal, the noise of the robotic arm. The whole recording has been speeded up by a factor of 60 to make it audible. So you could hear that actually the noise sources, in particular noise like a robotic arm or so, can be very loud and be the dominant signals that we see or that we see on the seismic recordings, and they may overwhelm, together with the wind, the actual Mars quakes that are of interest. So if you couldn't properly hear the video, or if you wanted to see this again, just visit the NASA page and you will find the video there. So now let's move on to the second instrument that is of interest to us, so the HB cubed, the heat flow and physical properties package. So that was also placed on Mars on February 12th. And the idea is to have a self-hammering device, a so-called mole, that penetrates 3 to 5 meters into the Martian regolith. So hammer itself down to take temperature measurements at depth to avoid the influence of, say, seasonal variations, for example. Now, these instruments were placed on Mars relatively close to each other, what was possible to do with the robotic arm on the lander, so they're about 1.2 meters apart from each other. Now, as I told you before, HB cubed is supposed to hammer it down into the subsurface, and actually it will need thousands of hammer strokes because the mole will just advance by millimeters ideally, and each of these strokes will generate seismic waves. So we could actually see this as an active source seismic experiment that provides us a unique opportunity to study the Martian subsurface. And this experiment actually provides us the opportunity to study the near surface, so the topmost maybe tens of meters, and extract elastic property models to infer on the geological structure, the composition of Mars, maybe also the geological history at the landing site. Understanding the elastic properties at the landing site is also important to understand the seismic noise that is measured by SEIS, to understand amplifications and other effects that we see. And knowing the regolith properties may be of interest also for future missions. So as some of you may know, at least as it is today, the mole got stuck actually already after the first hammering session at about 0.3 meters depth. And you see here on the left photo, once this structure, the support structure that was on the mole was removed, and we see the exposed mole here. And right now the InSight team is working on measures to trying to get the mole continuing its journey down to 3 to 5 meters depth. So in this presentation, I on the one hand want to talk about the concepts that we've developed, actually assuming that the mole would reach some depth, and I also want to discuss the results that we have obtained so far from the hammering, because it already tells us something about the elastic properties of the Martian subsurface. So let's first look a bit into the concepts that we have developed to analyze the seismic data. So what you see here is actually real data recorded on Mars, one mole stroke. You see that I marked here the duration of 1 second. So you see that this is relatively short signals from one hit of the mole. I also marked the time when the mole stroke happened. Now, to discuss a bit the arrivals that you may see, I'll just show for display purposes here, also to explain a seismic velocity model. So the first arrival that we probably see, or the first signal that we see, is the wave that takes the shortest time between the mole tip that we assume as a seismic source and SEIS. This first arrival can give us information about the velocity structure. But there may also be arrivals that actually are reflected at the subsurface at interfaces, and they may then arrive later in the coda and carry information about the subsurface structure in more detail. Now, in order to interpret the data, we actually reorganize the data into what we call a common receiver gather. So what we do, say, assuming that we had hundreds or thousands of hammer strokes that were recorded while the mole hammered itself down from the surface to a few meters depth. And we can arrange that data in this type of matrix form, where you see on the horizontal axis would be the recording taken when the mole is at a certain depth. And on the vertical axis, we see the time after each mole stroke. So for people working with seismic exploration data, that would be the way that we would organize our data for an analysis in common source gathers. Now, if you look at the different arrivals that I discussed before, and we see that the first arrivals would show up as the name says, as the first energy that we record. And we also see that the reflections from interfaces appear as coherent arrivals, but they show a different slope, so a different shape than the first arrivals. And based on this different shape that they show, or the relative move out, we can, for example, separate or identify and separate these arrivals. Now, what can we do with this type of data? As I said before, the first arrivals, they may give us information on the velocity model, and the reflections, they can be used for subsurface imaging. And this type of subsurface imaging is actually inspired by vertical seismic profiling, or reverse vertical seismic profiling, if you want so, because the source is at depth, to produce reflection images of the subsurface. Now, what I showed you so far is the concept, the ideas on how to analyze this data. Now, actually, these ideas were developed already after much of the mission planning was already done. So, because this analysis of the HP-cubed hammering signals was not foreseen in the original mission plan, it kind of comes as an opportunistic experiment, and with that, there are also a number of challenges that had to be resolved to realize that experiment. So one of the problems is that all the instruments operate on independent clocks, HP-cubed, SEIS, and the lander, and these clocks have temperature-dependent clock drifts that need to be corrected for. So we had to implement regular time correlation procedure to be able to really relate the different data types to each other. And then another challenge actually comes from the fact that SEIS was designed to measure Mars quakes. And these Mars quakes have a frequency content that is below 50 Hertz, or the acquisition flow was designed for frequencies below 50 Hertz. Now, from modeling and also analog experiments carried out on Earth, we actually expect the seismic signals generated by the hammering mole to have a much higher frequency content. That's illustrated here on this amplitude spectra that you see on the bottom right. So probably dominant frequencies are rather in the range of, say, 100 to 200 Hertz. And if we apply this nominal acquisition chain that would cut frequencies above 50 Hertz, we would lose much of the information. I'll illustrate that in a moment with a synthetic data set. So just to explain briefly how conceptually this acquisition flow works. So we have the data recorded by SEIS that you see here on the top left, that would be converted to digital information. Then anti-aliasing filters are applied to decimate the data that is then transferred back to Earth. And you see for a simulated data set that we acquire the data, but if we then decimate the data, as I discussed before, to have a maximum frequency content of 50 Hertz, we would lose much of the details in the data, and these images would be very difficult to interpret. So with this in mind, we realized that it is necessary to modify the acquisition flow to recover highest possible resolution subsurface data, ideally data that is very close to the analog signals, as shown here on the left-hand side for a synthetic data case. So what we came up with is a workflow where we actually avoid or omit the anti-aliasing filter. So we just only decimate the data and send back to Earth aliased data. And then we developed a reconstruction algorithm that would reconstruct the original data from these aliased recordings. And the reason why this works is explained here on this slide. So what you see here in the center, where I called aliased data, is a plot similar to the common receiver gather that I showed you before. On the horizontal axis, you see hammer strokes. On the vertical axis, we have the time after the hammer hit. But now the dots mark actually the samples that we have acquired. And you see this data, even though they are aliased, we see some linear structure. And you also see that actually the dots are randomly distributed if we compare one column to the next column. So we can exploit this linear structure in the data because the hammer hits are not changing significantly from one hammer hit to the next. And this independence between the sampling and the hammering to reconstruct the data using a sparseness promoting reconstruction algorithm. And this actually allows us to reconstruct data that has a frequency content up to a few hundred Hertz. So with this data, then we can actually carry out the analysis that I discussed before. Now let's come to the actual data that was recorded on Mars and look at the individual hammer sessions. So there were 4 sessions carried out so far. And for the last 2 sessions, session 3 and 4, actually the aliasing filter was turned off, as I discussed before, and data were acquired in the way that we can reconstruct the high frequency content. But also, as I mentioned initially, the mole tip, the mole was actually stuck at about 30 centimeters depth already during hammer session number 1. So that means if we come back to that type of common receiver gather that I showed you before, actually all the up to thousands of hits that they have recorded so far, we actually have recorded only data from 1 at that level. So we are limited in the type of analysis that we can do, or say this type of reflection imaging that I, for example, discussed, would not be so straightforward to carry out with this data. Nevertheless, what we did is arranging the data in this common receiver layout, so the reconstructed data, and pick the first arrival. So we see again on the horizontal axis data sorted by hammer stroke. The vertical shows you the time after the stroke, so T0, the black line, marks here now actually the stroke, and you see the picked first arrivals. Now they scatter quite a bit. This is likely due to uncertainties in the actual hammer time, so that because we still don't know so precise when the hammer actually hit the subsurface. Now with these travel time picks and the known geometry, we can compute what we call an apparent p-wave velocity. So just using time and distance to compute the velocity. And this gives us an apparent velocity of about 120 meters per second with quite some error bars. Now this velocity is probably reflecting the bulk velocity of the volume between the mole tip that we assumed as a source and the recording device size. Now this velocity sounds probably very low to those working with data from Earth, but we know first from Moon that the very shallow velocities observed for the regolith layer are very low, and the velocities that we see here, they're actually consistent with what we expect for the geology, so unconsolidated dry sands that are observed at the surface of Mars from the images taken being available so far. So with that, I would like to move on and leave Mars, hoping that the reason that the mole is actually stuck is not what you see here on this image here. And what I'd like to do is moving on now to the second part that I kind of see as an outlook type of discussion on what could be done in the future in terms of exploring planets and asteroids. And in particular, what I want to talk about here is the Pioneers project that has the goal to develop a new generation of motion sensor. So the motivation behind this project actually is to study the internal structure of planetary objects. So these are, say, planets or moons in our solar system, comets, understanding the structure, but then also the processes that form them, to also be able to understand how habitable worlds out in the galaxy or in the universe form. Then studying comets and asteroids, in particular, following the trajectories and understanding the orbits is important for planetary defense as well. So to be able to predict whether a comet could hit Earth, for example. So in a nutshell, the idea is to take the experience that the team behind Pioneers has from the InSight mission to Mars, but also the experience that team members have in the development of latest seismic instrumentation on Earth to develop a new type of sensor that is actually a 6 degrees of freedom sensor that measures translational and rotational ground motions. And the idea is to use this type of sensor to really enhance single station studies. And with the project, there are actually two kind of targets, two kind of directions that instruments could be developed. One is for planetary targets. So there we need very sensitive instruments because the signals may be very small. On the other hand, the small targets may be fast rotating comets or asteroids or moons that may need less sensitive instruments. Just remember from the moon study that I showed initially, the value that we have from this kind of additional rotational motion measurements in order to study the subsurface of a planetary body with just one station. Now, the applications that we have in mind are, on the one hand, looking at lander rebounds. So, when a lander hits or is supposed to hard land on an object, how it will be rebouncing, and finally come to its rest. Study the rotational dynamics of bodies, doing kind of assisting in navigation questions, but then also doing 6 degrees of freedom seismology. And I want to briefly explain what I mean by these different terms in the next few slides. So 6 degrees of freedom seismology means measuring the full motion induced by a seismic wave. So not only translational motions that we conventionally measure, but also rotational motions. The idea is to study the interior structure of planetary objects, and with these 6 component measurements really enhance the single station analysis. So this could be what you see a bit in this sketch on the left-hand side: improve Wavefield separation, better determine the incidence direction of a wave, analyzing the subsurface properties, or have an enhanced, being able to conduct an enhanced analysis of the subsurface properties, but also, for example, better locate earthquake sources and do improved seismic imaging. And then another aspect, if we measure rotations, that means we can also correct for tilt that may be important for certain classes of signals that we want to analyze. So the signals that are of interest here are obviously quakes, but also impacts, being that natural or artificial, but maybe also active source experiments similar to the Moon or Mars experiments that I discussed before. Then another application would be to follow the trajectory of a lander. And I show you here an image of the Philae lander on Jury. So you see on the top, actually the image is following the lander approaching Jury, and you see that after the first touchdown, the lander actually was finally coming to a rest at a different point, and knowing exactly the trajectory of this of a lander may allow to infer on the properties of the subsurface, the local gravity field, and may also help defining requirements for future missions. What is needed here are continuous records of acceleration and rotation, so kind of a navigation problem. Then another application could be, as I mentioned before, rotational dynamics. So that could be placing sensors on small or large bodies and actually understanding the orbiting properties, the rotations, maybe looking at tidal locking, moments of inertia, to really infer on the internal distribution of mass. And what is needed here are very precise measurements of rotation and translation. So with that, I would like to leave the solid bodies, if you want so, and move into space, and actually discuss in the last part of my presentation an experiment that is taking space as its laboratory. Specifically, I want to talk about gravitational waves using the LISA satellite constellation to measure gravitational waves and interpreting this satellite constellation as a kind of gigantic seismometer. So maybe before talking about LISA, I want to briefly introduce what gravitational waves are. So these are disturbances in the curvature of space-time generated by accelerated masses, a bit shown as illustrated here in this animation. So they propagate as waves at the speed of light, and they were first proposed by Henri Poincaré in the beginning of the 20th century, and later by Albert Einstein in his general theory of relativity predicted. And the interest in gravitational waves is that they, or the particular thing is that they provide a new way of studying the universe. So to complement studying dynamical astrophysical phenomena with commonly done with electromagnetic waves, and have a new way to study the universe. Now, the very first direct observations of gravitational waves were actually done just recently in September 2015 and published in February 2016. I'll show you here on the bottom the record of one of the LIGO observatories, and you see the waves that were recorded. And now the point I want to make here is the amplitudes of these gravitational waves. They're measured here as strain, so changes in the distance between long distances, and you see that these are very, very small amplitudes that we are looking at. So to the power of 10 to minus 21 strain. Now, the sources of gravitational waves are, for example, galactic binaries. So that means orbiting white dwarfs or neutron stars. It could be extreme mass ratio in spirals, so there can be a small stellar black hole orbiting a massive black hole. There may be emerging black hole binaries, or there's signals just from the very early universe. And now the challenge when studying gravitational waves is actually that all these sources are active at the same time. And what we record is, in particular for the galactic binaries, just the sum of thousands, tens of thousands or hundreds of thousands of sources that are active at the same time and emitting these signals. So the identification of a single source could a bit be seen like identifying a song being hummed at a very noisy party. And the challenge is really to extract that single signal out of a much larger noise that is called confusion noise. In that sense, not a noise like an instrument noise, but rather the sum of many other unwanted sources. Now, as discussed before, the detection of gravitational waves has so far been done with Earth-based observatories very successfully, as the Nobel Prize that the LIGO team won illustrates, or members of the LIGO team won illustrates. Now, LIGO is the Earth-based observatory is actually measuring in a frequency range of, say, 10 to maybe 10 hertz to maybe kilohertz range, and it's very hard to measure low frequency signals because the noise significantly increases. So noise means like seismic noise that is actually making it impossible to record on Earth low frequency signals. So the next step is to go to space develop instruments that can measure gravitational waves in space. And this is complementary in the terms of frequency content. We're looking now at the millihertz to maybe hertz range, but also there are different types of sources that can be studied with this type of satellite, or this type of space-based observatories. Now, ESA's idea is to send 3 identical spacecrafts to space in the early 2030s, and they will form a gigantic interferometer with arm lengths of about 2.5 million kilometers distance between the satellites. And they'll use laser ranging to determine the distances. And just to illustrate, because these gravitational waves have so small amplitudes, it is necessary to measure that at an accuracy of picometers, so 10 to minus 12 meters. Then you see here on these illustrations below, once the satellites are in space in the early 2030s, they will, the constellation will actually orbit in a kind of cartwheel type of motion around the sun, just lagging behind Earth. Now you probably wonder what is then the link to seismology, looking at the gravitational waves that come, for example, from these 2 emerging black holes. And actually, it's very striking to look at the analogies between the gravitational wave and seismological sensing. So first of all, the sensing principle is similar or is the same. So one is looking at the motion of a test mass to detect these waves. If we look at the waveforms, we see that there is some similarities. I'll show you here below an earthquake recording and a synthetic data generated for extreme mass ratio in spirals. And for people with a seismic exploration background, looking at these merging black holes that have a chirp-like signal that actually reminds us of fiber-size data. And there is another analogy or similarity. Also, seismic signals are actually dominated by signal, because the instrument noise may be so low that what we measure is just the sum of many different sources, and extracting individual signals is can also be a challenge in seismological work. So the idea, our idea now is to really take this recordings from LISA and applying seismological techniques, for example, array type of techniques to analyze the data. And I'll illustrate that with an example. So that's a recording of a binary. You see in blue the signal that would be processed from this one source, and in red you see the confusion noise, so the sum of all the thousands of other active sources all around. And you see here that this is the record of a whole year. So one possible approach is to split actually this recording of the 1 year into the recordings done by an array. So turning the orbiting LISA constellation into a seismic array, a circular array, and then use array type of processing to determine the source parameters, for example, the incidence direction. And you see here the result of using a grid search type of analysis to determine the incidence angle. So with that, actually come to the end of my presentation. And I just want to briefly summarize the key points that I've been talking about today. I should bring up here again the contents slide that I showed at the beginning. So I first talked about this reanalysis of the Apollo 17 seismic data. Just to illustrate that revisiting vintage data with new technology may be very valuable. So keep a copy of your data and check your archives once you have come up with a new technology. It may be very interesting exercise. Then this first active source seismic experiment on Mars is on the one hand by itself very interesting to study the near surface in a way that was actually not foreseen when planning the mission. But also there is a lot to learn from this exercise in terms of how to ideally design an active source experiment in space. And then I talked about more in a type of outlook, how new equipment is coming up, how new sensors are coming up. So developments on Earth very quickly percolate into space exploration, and in particular looking at this type of 6 degrees of freedom measurements, so measuring translation and rotation, is very interesting for these applications where you actually only can put one or a few stations at one point and need to extract the maximum possible information from one point. And the last part was talking a bit what could be seen as a new field of seismology, really looking at wave type phenomena and applying seismological techniques to help solving fundamental questions here about gravitational waves and the formation of the universe. So that I'd like to finish, and thank you for your attention, and I'm happy to take your questions.
Okay, thank you, Cedric. That was a very interesting presentation. Those of you who are attending, if you'd like to ask questions directly, you can raise your hand in the webinar interface, and I will move you so you can ask your questions. Alternatively, you can enter your questions in the question and answer box, and I will pass those to Cedric. All right. So there is one question about the derivatives that you're taking from the Apollo 17 moon data with regards to the geophysical spacing and the kind of uncertainty that you encountered with that data. Can you speak to that a little bit?
Mm-hmm. Yeah, that's a very important point in doing rotational or this type of array-derived analysis. So obviously one of the problems is the spacing by itself. So this should be at a fraction of the wavelengths we're looking at. So with this large spacing that we see on Moon, we're actually only able to look at the very low frequencies, not to run into problems with aliasing. And then obviously the uncertainties in knowing the locations maps into the array-derived rotation estimates. So in the case here, we think because we are primarily interested in actually the arrival of rotational energy, we are not that much concerned about the absolute amplitudes of the rotation rates, even though if you look at the slowness values that we derived, actually they are sensible. But I mean, there is a certain there is indeed an error that comes into that just from not precisely knowing the location. So what we did here is looking at the records that we had from the Apollo 17 missions. Recently, this has been revisited, and the locations have been improved a bit, but we didn't redo the analysis yet. I hope this answers your question.
Okay, yeah, thanks. Also, I guess there's a question with regards to the types of material found on the Moon versus that on Mars, based on the, at least the initial data from the seismic experiment on Mars. Can you discuss a little bit about the differences?
If I understood you correctly, so you're wondering about the difference between what we find on Mars compared to Earth in terms of material.
Yeah, Mars to the Moon.
Mars to Moon. Okay. So
Sorry.
one of the important differences is that, I mean, there is no the sediments on Moon are dry. So what you're looking at is completely dry sediments. And there is no atmosphere, and in contrast, on Mars we do have an atmosphere that has probably also some influence on the material properties that we observe. So other than that, I mean, we're looking at very fine sand that probably formed from all the impacts, and say assuming that the velocities in both cases are very low, so it seems reasonable at the first guess from what we know from modeling, for example.
Okay, thank you.
I have a question about your decimation. So when you discussed it, I didn't understand properly whether, I understand that you have a random sampling or non-regular sampling, but is it different for each trace, or is it the same for all of them, and then you do the reconstruction with sparse constraints? What kind of sampling is it in your decimation?
Mm-hmm. Yeah, I see. So it's important is, I mean, it's a regular sampling in terms of the analog to digital conversion is just running continuously and doing a regular sampling. But what is irregular is the timing between the hammer strokes and actually the sampling mechanism. So they are not synchronized. It's not like in an active source experiment where you would press a button and you would start recording and firing off the source at the same time. So
yeah, that I understand. My question is more about, you are decimating the data. Mm-hmm. Is the regular type of decimation?
Oh, the type of decimation is just picking every so-and-so sample. So that's it.
Regularly?
Yeah.
Okay. Thank you.
Okay, do we have any other questions? Well, it doesn't look like we have any additional questions, which is pretty good because we're a little bit coming close to running out of time. I'm curious, is there a working group that you know of, say, that's attached to the EU or the EU's space mission as well as NASA that we might not be aware of? In addition to yours?
I mean that there is there are at the end a series of research institutions working in space and space exploration. I would think that I mean this type of really bringing controlled active source or controlled source experiments into space, I'm not aware of too many groups that specifically work in that direction. So there has been the German Space Research Agency, the DLR. They have they conducted this experiment on comet Jury that can be seen as a bit of a active source experiment. But I would say other than that, really in doing pure exploration comparable to the exploration on Earth, I'm not aware of too many groups working in that direction.
Okay. All right. All right, we have someone who wants to ask a question. I just moved them. So they should be All right. Okay. So, Paul, if you'd like, you can unmute yourself and ask your questions directly.
Hello, we're muted.
Yeah, go ahead.
We are muted. Oh,
You're good. You're good. I can hear you, Paul.
Kun je dat even doen? Ik heb mijn bril niet. Het is goed. Je kan praten. Wait, can you hear me?
Yes, I can hear you.
Okay, great. Okay, so this is Roald van Borselen from Delft. I have a question. So with the ambitions of Elon Musk doing a lot of increased traveling in space to the moon or Mars, do you have any ambitions to work with him? And what kind of experiments do you foresee? Or what kind of new opportunities do you foresee if that's actually going to happen?
I think that's an interesting question, because I mean, commercial or people like Elon Musk or commercial missions may become more and more to be seen, and now happening in the near future. So I think an important point or an interesting opportunity is actually to bring instruments to, say, Moon, for example, with Elon Musk, and then place seismometers at places, so have lightweight instruments that actually could go as a payload with another mission and be placed there. And I think, for example, extending a network on Moon with the help of Elon Musk or others would be a great thing to do.
And what will be your ambition then? What kind of new measurements would you like to take? What will be the driver for the research?
I mean, the drive, if you want to go to Moon, there is still a number of open questions on the structure of Moon, just of the entire body, to understand the deeper interior, understand, for example, sources of moonquakes within Moon. And if you think of future missions or even having manned missions to Moon, the question of where there is water ice, for example, is very important. Whether I mean, such a commercial mission would be the ideal way on starting to explore specific areas on the Moon is probably another question. I guess, I mean, if you have commercial missions to Moon that would be willing, I mean, so it's probably a question of price, to bring another seismometer to Moon, that would already be very interesting to build up a network to see, just to better understand the internal structure. You see, so far we have 4 stations, and if you compare that with Earth, where we have many stations, and on Earth we are able to do 3D tomography and so on. So it would be great to do a step towards resolving the internal structure of Moon in greater resolution already.
Okay, and you're already in contact with Elon Musk, or?
No, I'm not.
All right, thank you very much.
All right, thank you. All right, any additional questions? You can raise your hand in the interface or put them in the question and answer box. All right, well, I think we are just about done for today. It was a very interesting presentation. I liked some of the questions. They were very good and nice responses. So with that, thank you, Cedric, and thank all of you for attending the SEG Europe Regional Advisory Committee's webinar as part of our webinar series, Geophysics for Today and Tomorrow. Please look for our social media posts to register for next month's interesting talk. And thank you again for attending today, and thank you, Cedric. Have a great
day. Thank you.
Thank you.